This is question 52 from the GATE 2021 EE paper. The question deals with a Schmidt trigger inverter and its output has been connected back to the input. We are asked to find out the frequency of the oscillator shown. Underneath the question, you will find the title of the NPTEL course or video relevant to this topic. So before we start, a little bit of background into a Schmidt trigger. So in an inverting Schmidt trigger, all you need to know are the values of input high, input low, output high and output low. And the way it behaves is once Vin crosses input high, like so, Vout can be said to be at output low from then on. Even this is a crossing event, but since Vout is already at output low, it will just continue to remain so. When will it change? It will change at the next crossing event on the other boundary, which is input low, and it will change to output high. So all you have to do is to look out for where the input crossing events are, and you will be able to determine what the output is for the Schmidt trigger. So let's go ahead to solving the problem. Let's assume that the input Vn has just had a crossing event, right? That is, we are at t equal to 0 and Vn is at input low, which the problem says is 1.6 volt. Right? So for this crossing event, the output will be at output high. So the idea is that the equivalent circuit is the Schmidt trigger is outputting an output high, which the problem says is 5 volt. So this is what the Schmidt trigger is outputting, and through the resistor we have it charging the 47 nanofarad capacitor. So what will happen? It will keep charging it towards 5 volt. But as soon as it hits the input high crossing threshold, the output will change in response to become 0 volt. And what will happen? You will now have capacitive discharge. It will try to discharge till 0, but it will reach the crossing threshold and cause the output to go up to output high again, causing the cycle to repeat. Thus, this is an oscillator. We will split the time of operation as one of length t1 and one of length t2. So the period is t1 plus t2. I have split the solving of the problem into two regions, 0 to t1 and t1 to t2. From 0 to t1, we can assume that Vn of t is equal to Vn of infinity plus Vn of 0 minus Vn of infinity into e power minus t by tau. This is just the RC charge-up equation, where tau is the time constant R into C. From the RC charge up, we know that the Schmidt trigger outputting a 5 volt means Vin of infinity is 5 volt, and Vin of 0, because the input low is 1.6 volt, Vin of 0 is 1.6. This is e power minus T1 by tau, because we want to find out what T1 is. In our analysis, Vin of T1 is 2.4, which is input high. So if you actually work out this and invert the exponential, you will find that T1 is 126 microseconds. Similarly, for the T1 to T2 portion, if we remap T1 as T equal to 0, we can again write the expression as Vin of infinity plus Vin of 0 minus Vin of infinity e power minus T by tau. This is with the remapping of this to 0. So whatever value we get, if we just do T1 plus that, we will get the final time. So Vin of T2 is equal to, what is Vin of infinity? Well, Schmidt trigger is outputting a 0 volt, so that's 0. Vin of 0 is 2.4, that is input high, and e power minus T by tau. Vin of T2 is input low, this is 1.6, is equal to 2.4 e power minus T by tau. But remember, what we want is the time period T, which is T1 plus T2, which is approximately 316 microseconds. And the frequency F is 1 over T, which is approximately 3164 Hertz. Thus the answer is 3164.